Alright, in this video, 5.5, we're going to talk about continuous random variables. Prior to this, we talked about discrete random variables that had little packets of information, like you could get 0, 1, 2, 3, or 4, or 5 in your result. 5 children, 4 children. There were no decimals. There was no in-between. So when we talk about continuous, we're bringing up the idea of there's values between 1 and 2, and 2 and 3, and so on and so forth. Alright, so below is a relative frequency histogram of the scores of all 7th grade students in Gary, Indiana on the vocabulary part of the Iowa test of basic skills. The scores are grade level equivalents, so the score of 6.3 indicates the student's performance is typical for a student in the 3rd month of grade 6. Alright, the histogram, notice, is roughly symmetric, and both tails fall off smoothly from a center peak. There are no large gaps or obvious outliers. Okay, so notice it's just really smooth all the way. There's no gaps, there's no breaks, everything has a value. So suppose that we choose a Gary 7th grader at random. Let X equal that student's vocabulary score. So let's say, what's the probability that the score is less than 6.0, like less than 6th grade level? It's the probability that a randomly selected student earned a vocabulary score less than 6th grade equivalent on this test. The area of the shaded bars in the relative frequency histogram represents, in A, right here, represents the proportion of students with vocabulary scores less than 6, okay? This is the 6 bar, right? And so all of these bars this way are less than 6. The smooth curve drawn through the tops of the histogram bars in B is a good description of the overall pattern of the distribution. We call this a density curve. Okay, when all the bars are really close together and everything's accounted for, there's no gaps, craziness going on, this is called a density curve. The probability distribution of a continuous random variable is described by a density curve. A curve that has two qualifications. One is always on or above the horizontal axis. Okay? And it has an area of exactly 1 underneath it. All right, now, a probability distribution curve can be the good old symmetric curve like you're used to. It could also be just a basic uniform curve like this. It sits above the x-axis and the area is equal to 1 underneath it. This is also a continuous random variable density curve. They could look either way. This one is the one you're going to encounter the most, but this one does happen sometimes. Okay, balance point, that's a key thing. This figure illustrates the idea for mean of a continuous random variable. So if I have these different curves, I want to find, okay, this value is the mean. If I put it here, is that balanced? No. If I put it here, is it balanced? No. If I put it here, is it balanced? Yes, it is balanced there. So the median of a continuous random variable is the 50th percentile of the probability distribution. It's like half and half. Where would you split the distribution half and half? So write these definitions down for me. Okay, balance point is the mean, and cutting the distribution in half is your median. All right, the median of a symmetric probability distribution is right in the middle. Like, look at A right here. It's right in the middle. A symmetric density curve balances at its midpoint because the two sides are identical. So the mean and the median of a continuous random variable with a symmetric probability distribution are equal. Okay, so notice they're the same if they're symmetric. Now, it's not so easy to spot the equal areas point on a skewed probability distribution. So in a right skewed distribution, the mean, remember the mean is non-resistant, the mean is greater than the median because the balance point of the distribution is pulled along the right tail. It gets pulled toward the tail. So the mean gets higher than the median. It's pulled to the right. And you can imagine if it was skewed to the left, the mean would be pulled to the left of the median. Now, a normal distribution is described by a symmetric, single-peaked, bell-shaped density curve. Okay, both of these are normal. Any normal distribution is completely specified by two numbers. We describe it by the mean and its standard deviation. So all normal distributions have the same overall shape. They're symmetric, single-peaked, and bell-shaped. The mean is located at the midpoint of the symmetric density curve and is the same as the median. We just talked about this. The standard deviation measures the variability, the width of a normal distribution. So make sure you catch that. Standard deviation measures variability or the width of the normal distribution. So let's try some problems here. Biking accidents on a level 3-mile bike path occur uniformly along the length of a path. Let y represent the distance from the start of the path at bike path at which a randomly selected accident occurs. The figure displays the density curve that describes the probability distribution of y. All right, so this is a density curve. It is symmetric, but it's not a normal curve because it's not mound shaped. It's just like a rectangle. And the reason it's a rectangle is probability of having an accident is the same, right? At 0, 1, 2, 3, and everywhere in between along this bike path. So the question is, why is this probability distribution of y valid? Okay, well, if you recall, there were two reasons that make things valid. Okay, so the first reason it's valid is because the area under the curve is above the horizontal axis. Okay, that's the first criteria. The other criteria is that the area under the curve has to add up to 1. Okay, and we know that it does because think of this as a rectangle. Think of rectangles as length times the width, and you need area, right? So if the length of this is 3 times the width, which is 1/3, 3 times 1/3 is 1. So it has the area is equal to 1. And so those are the two criteria that have to happen for this to be a valid probability distribution. Now, part B. Elias property adjoins the bike path between the 0.8 mile marker and the 1.1 mile marker. So find and interpret this probability. What's the probability the bike path or the accident is going to happen between these two? Okay, so this is 0.8 right here, 0.11 is right here. So we're looking for what's this probability area. Okay, so we need to know, okay, what is this value? Think of our area of a rectangle. Think of this times this. All right, so let's think about this. That bottom area would be 1.1 minus 0.8, which gives me a 0.3 value. Okay, so this part is 0.3. This length right here is still 1/3. So 1.3 times 1/3 would give me a probability of 0.1. Let's put it in the calculator. So that's the finding part. Now I have to interpret this. We would say the probability that an accident will occur between the 0.8 and 1.1 mile marker is approximately 0.1. Okay, full sentence, context, and you say about for probability. You can say about or approximately, whatever you want. All right, that's example 1. All right, the probability distribution of a continuous random variable is shown. Identify the location of the mean and the median by letter. So we notice that this is not a perfectly symmetric shape like this. If it was, then we know the mean and the median would be the same, but that's not the case. So the first thing we need to do is find out where is the median. Okay, so remember the definition of median means it splits it into 50-50, right? So let's look at our values. A splits the data here. The area left and right of it don't look equal, so I would throw out A. If I look at B, to the area left and right of B, I think B is more likely than C, so I would go with B. So I would say B, because there's equal area. It's the equal areas point in the distribution. All right, so identify median first. Now, to find the mean, remember, mean gets skewed. Mean gets pulled towards the tail. So since this is right skewed, the mean is going to be to the right of the median. So if B is the median, what's to the right of it? Well, C. C would be the mean. So C, because the mean is greater than the median due to the skewed shape. You could say right skewed, that's fine. You just have to mention that the distribution of weights of a 9-ounce bag of a particular brand of potato chip is approximately normal, with a mean of 9.12 ounces and a standard deviation of 0.05. Sketch the probability distribution. Label the mean and the points that are 1, 2, and 3 standard deviations from the mean. All right, so let's draw a line. Standard normal curve. All right, the mean is right in the middle. So we say 9.12 ounces. And we label this, we'd say the weight of a 9-ounce bag of chips. All right, now the next thing it says, label the mean and the points that are 1, 2, and 3 standard deviations from the mean. Well, to find one standard deviation out, I'm going to take the 9.12 and I'm going to add one standard deviation. It's 0.05, which gives me 9.17. So 9.17 is one standard deviation higher. Now to go 2 standard deviations higher, what am I going to do? I'm going to add another 0.05. That gives me 9.22. This is 1 standard deviation out, 2 standard deviations out, and then 3 standard deviations out. Hopefully you get that you would be taking the 9.22 and adding 0.05, which gives us 9.27. Okay. So that's adding 1 standard deviation. So to the left, we have to subtract 1 standard deviation. Okay. So here, I'm going to take 9.12 and I'm going to subtract 0.05. And I get 9.07. Then I subtract another 0.05. And that gives me 0.02. That's 2 standard deviations to the left. Then if I subtract another 0.05, I get 8.97. Hopefully your drawing will be more spread out and easier to read. But this is what they're looking for. They look for the normal curve with the mean in the middle, and then you add your standard deviations to the right, and you subtract them to the left 1, 2, and 3 times. Make sure you don't forget to label your axis. All right? Hope this makes sense, and we'll talk some more in class.